A of y. So here I write it in terms of generators. And here I have equations. And this is still too general. However, in special cases, say in the case k equals to 1, I understand, say, k equals to 1, I understand that I have polynomials, and here ideal generated by one function, and this is called hypersurface, and this is understandable. In particular, I could study the question of deformation. They correspond to change of f of y to f of y polynomials. So deformation theory is understandable. General solution is not that understandable. General theory. And it's interesting to note that we have similar situation in quantum field theory. In quantum field theory, we have defining equations. Defining equations that I schematically write like this.
The camera lost focus.
1 second. Maxim?
Now it's okay.
So this is not constructive. So how can we find this solution to this equation? In dim x equals to 1, we have instead f of t1 and this is constructive. We say f of t is exponential th. Now, nevertheless, okay, it is not constructed. However, maybe we can get deformation theory. And here, an interesting thing happens. Imagine that we can enrich the theory, the functorial QFT, by local observables. Sometimes people call defects. So what do I mean by enriching functorial QFT by defects? So originally F belonged to homomorphisms of V in, V out times functions on geometry. Gamma in, gamma out. Functor takes gamma in to V in. Functor takes gamma out to V out. Now I want another thing. I want to have a point P. And I want to say that this would be cobordism decorated by a point. Okay? Now, I want to associate to point P vector space D. That is space of defects. That's why it's called D. And then I like the value of the functor on cobordism decorated by a point to belong to D star times homomorphism V in, V out times functions on geometry times differential form say differential form on X. Now, what are the conditions? And condition is like before. I have a point and I cut. Here I have gamma 1, gamma 2. Here gamma 3, gamma 4. Then I still would like to demand factorization condition. And factorization condition is that f applied to this is f applied to this composition with f applied to the second half. You see, the number of components here and here could be different. I just took this for example. Here number of components of gamma in and gamma out is 2, just for example. And here we have V medium. Sorry, here we have gamma medium. And here we have gamma medium. And this is gamma medium out. And this is gamma medium in. And we have this composition. Now, I'll tell you canonical statement, but it's a kind of deep statement. Given D belonging to D, we can have a deformation. We have of Functorial QFT in the following form. F is going to F plus epsilon delta F. And delta F is integral when P belongs to X. Then I contract things with D. Sorry, let me call it phi. So I contracted here. And here I write the value of the functor on on this. And I integrate. And the claim is that this is a deformation of functorial equations. When it's written like this, it's pretty not obvious. Idea of the proof. Idea of the proof. Consider an integral here. Here we integrate p over x. Here we have integral. Here p sits on x1. On x1. Plus integral of x2. Equations on deformation. So how to write it down? Equations on deformation. We had FF equals FF. Now, let me call here G1, G2, G1 prime, G2 prime. So it is functoriality equation. Now let me study deformation. Plus f of G1. And here I have delta f of G2. Equals this thing. Now idea is to take delta f of G1 as an integral over x1 of f of G1 and also phi at point P. And here I have f of G2 plus second term. And terms would come together. So it is the idea. However, idea is good when this idea could be illustrated. So let me, you see, it's kind of complicated thing. Let me illustrate it in a constructive way. So how it works in d equals 1 case. we have e to the minus ph. F of t. Now, deformation. Corresponds to h going to h plus epsilon phi. So deformation is e to the t h plus epsilon phi.
Why we deformate Hamiltonian and not deformate exponent?
Because we know that that functor is always exponent of t to some h.
So we can consider deformed functor as something, some exponent. Okay.
So all functors correspond to exponents.
Okay.
So the difference is just difference of Hamiltonian. So now it is easy to show that this object is e to the th, and here I have the first term, and then the second term is epsilon, integral from 0 to t, e to the t minus t tilde h and here I have phi. So phi belongs to endomorphisms of L. E to the t tilde h. So it's a mathematical statement. And then how do we understand this object? Here we have phi. Here we have interval t minus t tilde. And here we have t tilde. And it's exactly functor enriched by a point. Why? Because we can write down equations. Equations for enrichment. So they basically say that if we cut here, so enrichment is given by things that is inside this exponent so this corresponds to an interval of the length t that has this point in the middle, this point enrichment, p. Coordinate of p is t tilde. And this thing solves equations for enrichment. So you may call it, so basically it means that if you have phi standing here, then you may cut like this. T tilde equals T tilde 1 plus T tilde 2. And then functor enriched I would say T tilde equals to the product of the functor enriched T tilde minus T2 tilde. And here composition with F without phi of T2 tilde. So this is exponential, and this is also exponential. And here we have a general statement, illustration of a general statement, that the deformation to the first order is given by enriched functor, enriched at a point. And then the space D is just endomorphisms of the space L. One should just have a look at these formulas and see that they actually correspond to the pretty geometric procedure of cutting this interval into two pieces. Meanwhile, let me prove this mathematical statement for completeness. The easiest way to prove it is to take derivative at t. To prove, take derivative in t. If I take derivative of t in the left-hand side, I will have h plus epsilon phi. On the right-hand side, I have h coming from this term. Plus, I take derivative in t. So first I differentiate the upper, the limit of the integral. And here I have e to the t minus t tilde h by e to the t tilde h. But then I also take derivative here. And when I take derivative here, I have this integral. Here I have dt tilde. Then the idea would be to see that here we have total derivative that we don't have. Okay, so you may complete this proof as a homework exercise. Home exercise. Proof. Prove this statement. Okay, I feel that I need to make a break. So questions, please.
Я правильно понимаю, что мы сейчас пытались доказать, что деформированный f это тоже функтор?
So what you are trying to get? We are trying to compare this thing that is a deformed factor with this thing. The right-hand side.
Нет, я понял, что мы конкретно тут пытались доказать. Я пытаюсь... Вот там было написано некоторое утверждение общее про f любой размерности. Что
Yes.
последовало
So here idea is that if we take something local and integrate, then you'll get a deformation of the functor.
and non-trivial statement that it's two functor.
Say it again, please.
Where is non-trivial part of statement? There is that f plus delta f is two functor.
So the non-trivial part of the statement is that f plus delta f is also a functor.
Oh, yes.
So to be a functor, you need to solve quadratic equations.
Mm-hmm.
And then the question is it true that when you do very particular deformation of f, it will still be a functor in the first order in deformation?
Mm-hmm. Okay, I understand you. Thank you.
And here is an example in the one-dimensional quantum field theory that is completely doable because we have complete mathematical understanding of what the functor is. It is this.
Okay, thank you. Yes.
So this, in particular, answers to the question, what are all functors? And the idea is, take one functor that you like and study deformations. Okay. Now I'll have a 9 minutes break. There is a construction. That I'll call construction of the point enrichments from the functor itself. construction of the point enrichment from the function itself. Idea is the following. Take x and then glue here disk, glue a cap. So idea, glue a cap. So we will have something like this. Small hole. So behave like a point. So this is the idea. Now I'd like to give definition or construction. Consider a disk of radius r. Cut out disk of radius r small. So we have an annulus. So functor apply to this annulus r may be considered an element of V star r. So V star r corresponds to incoming boundary SR. And here is outgoing. Times VR times. So times V times the function on the metric. That is functions on R plus times R plus. So here I have R small and here I have R capital. Now consider a family psi r of elements of VR such that contraction of psi r f annulus r such there exists a limit as r small going to 0. We will call such psi r a pre-observable. I write here as pre-observable. If the limit not only exists but equals to 0, we will call such psi r a null. I'll call it like this, null pre-observable. There is a space, local observables is a coset, set of pre-observables moduli null pre-observable. So I call them local observables D. Now, new concept. F R. Now only one R. D at 0. So it's a new concept. Is the following. I'm sorry. So in this case, given a local observable, I will define its value at 0 as a element of VR. According to the following formula. Psi R contraction with F annulus R and I consider limit when R is going to 0, and this definitely belongs to V R. So this is a representative of a local observable. And here is the state. So here I come with a new notion. This limit as R equal to 0, I psi R F N R capital R small, I will denote as phi at 0. So it's a factor that corresponds to a disk and a point. So this limit is this. And of course it belongs to VR. So it is defect at 0, defect phi at 0. And phi, sorry, and local observables is this space, pre-observables over null pre-observables. So having phi, I define what I have here. So phi is actually class of equivalence of such sequences. Remark. From phi or the disk, we can get phi at any point on X. So suppose I have something with a boundary, and then I want to understand what phi at P is. What this could be. I just cut a disk around. Disk of radius R. And consider this being the result of the following gluing. Glued to the disk with phi inserted at point P. So in this way, we get enrichments at points. Now it looks pretty abstract, but during the course, we would come to very particular examples. And you will see how all this is working out. So answer, I cannot upload the record because I have no right to record and there is no recording.
There were recordings, so someone did it.
Okay. So then please send the recording to U, okay? Yes. So let us see that in quantum mechanics, we are actually getting what we expect to get. Sorry, quantum mechanics is one-dimensional physics. To get local, to get something local, we do the following. We cut out. So this is R capital, and this is K2R capital, and this is 2R small. So here I have space L, 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 and L. So annulus is, annulus has 4 boundary components. L star. So these two correspond to what was called VR, and these two correspond to V star R. So that's why V star R is actually L star times L. Unusual case. It's because the boundary of a disk in dimension 1 has 2 components. So phi is just endomorphism. So phi just belongs to endomorphisms of L. Okay. Now, let me make several remarks. Remark number one. Observable or defect, better called defect. Defect obtained above may have non-trivial properties under diffeomorphism of X. In order to use it in deformation of the theory, we may use data from geometrical enrichment. Once again, in D equals 1, phi that belongs to endomorphisms of L is A not is corresponds to the fact. Corresponds to the fact. In order to write down here, we have no defect plus epsilon. And here we do the following. Here we put phi as point d tilde. However, we integrate one form where dt tilde came from geometric enrichment. So in this particular case, interval enriched by one form. dt tilde. So that's what happens. And to write down this nice formula, we need to take it into account. So it was remark number one. There is remark number two. In second order deformation, points P and P prime, this double integral may diverge when P is going to be prime. And this is a source for ultraviolet divergence. Okay, now remark number three. One can define OPE in this language. In the following way. Put here R capital. Put here R small. Put phi 1 as the middle and put phi 2 as the point R over 2. Now here consider pre-observables and limits. And in this case, what you will get, you will get concept, notion of operator product. It's called like this. So it was remark number three. Remark number four. In the definition, one may replace point by any figure. In X. So what will be the procedure? So consider this This is some complicated X. Okay? So this is X. This is something, say, curve. Or just figure. Figure gamma in X. Then consider the space let gamma epsilon be the space of all points in X such that distance between X and gamma is less or equal to epsilon. Consider X gamma epsilon. That is X minus gamma epsilon. Boundary of X gamma epsilon equals to the boundary of X joined with the boundary of what? Of X gamma epsilon. So here is the picture. You're just cutting out tubular neighborhood and you get extra boundary component. Now define pre-observable as a family psi epsilon that corresponds to V of d x gamma epsilon. Sorry, d gamma epsilon. Sorry, misprint. Such that I psi epsilon, and here I have functor applied to x gamma epsilon exists. Then you may define similarly null pre-observables. All the same plus limit equals to 0. And then new concept figure observable or the fact. It's a space of null of pre-observables moduli null pre-observable. and the gem. So it is clear having figure observable I call it O. It's type figure 5 to get functor x O A5. Function on geometry. And it also depends on figure. So why I'm writing all these complicated things? It's because later on we will see that that Wilson line Hoft line are both observables of this type. However, we will see it later. So today we don't have a recording, so I wanted to be short. I know that this would, that later on, when we will go to particular models, I will do these steps in these models. Okay? But my main point today was that one can define everything without going to particular model. My claim is that this is a proper mathematical language to define quantum field theory. And other models are just realizations. So, any questions? Maxim? Hello?
I need to think about it before I ask some questions.
Okay. Okay, that's it for today.